Okay, so right now we're going to look at gate manipulation. And basically the idea is that we're going to be given a target that is somehow hard to get. And we're going to say, okay, you have to represent some simpler function with that hard to get target. I find that usually when you just try to do the problem, I mean, you get a feel for it, but basically you find yourself doing a lot of mental gymnastics or a lot of diagrams that seem to go nowhere. So I find an easy first step, once you kind of get the idea for, like, okay, what tools might I need, you look for an easier target where you add some sort of simpler tool to kind of soften the constraint. So hypothetically, this exercise is, okay, try to write these functions using only Nand gates, which is kind of tricky. So, you could try it first, but you might kind of seem to think, okay, actually, if I can use an inverter, that makes things a lot easier. And let's look at why that is. So we have a Nand gate, and to refresh, not and means that when A and B are both and, that's going to be false. So we're looking for all functions that give you not and, not A and B. So 1 and 1 is going to be 0. But all the rest are either or false, or just not both. So then those are all ones. And then you have your standard A and B function, and you have this sort of truth table. Now, if you look at both of them, you might see a pattern, and it's that 1, 1, 1, 0 is the exact opposite of 0, 0, 0, 1. So you can see how, okay, this is actually kind of easy. You just say AB equal to A NAND B inverted. And the diagram for that would be the NAND gate, and then you invert the result. And that's your A and B. Okay, let's look at A or B, which is a little trickier, but still should be okay. So here we have A or B, and we see that, okay, we have the 0 in the wrong place. So we have to do some sort of manipulation with A NAND B. So if we look at the statement A NAND B, we're saying, okay, we can invert things, and we've already inverted the whole phrase. So, okay, maybe we can try inverting one literal at a time and see what happens. So let's try to do A prime. Now, A prime is basically the opposite of all of these. So that's 1, 1, 0, 0. Hope that's clear. And then that's B. And so A prime NAND, let me keep it color-coded, and B, so this truth table should come out to, well, let's see, we have the and there, so that's going to be false, and all the rest are going to be true, because we don't have 1 ones in any other row. So great. Why do I say great? Because this is not actually what we want. But it's interesting because even bad information or incomplete information might help us for future manipulations. And in this case, it will directly help us for the other manipulation. But it's good to keep in mind. So when you go through and play around with these, the key thing is that on a lot of your errors, you will get a sense for how certain gates match up and truth tables match up, and then you'll be like, oh, I saw this pattern just a little bit before for another problem, so maybe I could just apply it for the one I'm doing right now, and something like that. So you give yourself, your brain, the connections for it to make. So, okay, so that's not working. Let's try something else. Let's try, what if we do both of them? Now, why do I say both of them, and why not A, B prime? Because I have the feeling that if it's symmetrical, the 0 is going to switch out here. But that's a hunch. You would have to work it out to verify it. So, okay, we have A prime, and B prime. And A prime looks like this, and B prime, you look at B and you get the opposite. So 1, 0, 1, 0. And you look for the columns that match, particularly the rows that match in ones. And we have only one row like that. And so that's going to be your false. And all the rest are going to be true. And sure enough, that's what we wanted. Great. So we're making good progress. We can say A or B equal to A prime and B prime. And then we can draw the diagram if we wanted to. And so we negate each one first. And then we hook it up to the big Nand gate. And that's our A or B. Great. Okay, so now we move to A implies B. Now the truth table for A implies B, if you took discrete or proofs, it's basically, you have to look at A implies B as a whole statement. It's basically saying if B is not true and A is true, that this whole statement falls apart. If B is true and A is not true, that's not, the statement itself is still not invalidated, so it's still a valid statement. Another way that's referred to as, and you can look this up because it's too much to go into, vacuously true. So that's something if you're curious. But basically, this truth table is legit, and this statement, when A is false and B is true, A implies B is still true. It's just something that one has to get used to. And after a while, it starts making sense. But either way, that's our target. And actually, we have this kind of dangling 0 in the middle. If we look back, it kind of looks like this. So my spider senses are tingling here. I'm not Spider-Man. And I feel like, okay, if we just make the B inverted instead of the A, we're going to get something close to this, if not that exactly. So let's try it out. Drum roll. And for B, we invert the 0, 1, 0, 1 to get 1, 0, 1, 0. And sure enough, the one row is here, and it's false, and the rest is true. And we have this being true, matching. So we can say A implies B is equal to A and B prime. Great. Now, if you think about it logically, this is saying, okay, if you have A for sure, and there's a B prime, you can't, it's like you can't have A not imply B, right? So that's what the NAND is about. It's just it's kind of like a double negative, and that's the logically legal way to say it. Let's draw a diagram for it. And well, the A is fine, and then we invert the B, and we put it all into an AND gate. Great. Okay, now for the harder stuff. Let's look back at our target truth table values. So A and B, A or B, and A implies B. Now we have to just get that with NAND gates. This is the hard bit. So these are the values, A and B, A or B, and A implies B. Let me just make sure that was right. Yeah. So now only using NAND gates we have to pull for this. So let's actually think, before diving into this, let's think of some permutations that we can do. Because then we can cross them off and we can see if we're getting warmer or colder and aim towards a sort of goal in a methodical way. So we have A NAND, and what if we do it with A NAND B? That's a sloppy D. Yeah, what if we do it A combined with a whole NAND? Or maybe it's A NAND B. Maybe something like that. Well, what else could we do? Well, we could try A NAND B NAND A NAND B. Okay, that's another possibility, but that one seems it seems excessive. It seems like maybe we skipped a step, because actually this is using 3 NAND gates and these are using 2. Is there any more permutations with 2? And there might be. We didn't write A NAND. Sorry, I'm not color coding. A NAND A. We didn't write this because, well, we still need the B somewhere. So that I just took it out, even though that is a possible permutation. But this idea can be carried into these, and maybe you can have some sort of A NAND A NAND B NAND B. Maybe something like that. Or maybe, yeah, let's try these much, and then we can try to think of more permutations if we're really not getting anywhere. So okay, let's try A and then A NAND B. So this is, I'm just going to copy and paste because this is a lot of writing. I'm going to minimize it. B size. Okay, let's try this table. Now, A NAND B, you might remember from all the slides back, is 1 1. Come on, pen. 1 1 1 0. So let's try that. 1 1 1 0. And let's see where that lands us. So remember from before, the 1 1 is going to be false, and all the rest are going to be true. Now, is that in any of our desired? Yes. Great. So we can say A implies B is equal to A NAND B, which is very convoluted, but it is only using NAND gates. So that would look like A, so we work from the parentheses outwards. So we have A, B, we have some sort of a NAND gate, and then we have A connect to this output in a NAND gate, like that. Okay, so that's great. We can cross this one off our list. Perfect. But also we can, from this one, we can deduce that we got, since we got this kind of result, B NAND, the same A NAND B, is probably going to give us the opposite, which is not what we want for this. So I'm just going to put like, probably, I'm not going to fully cross it out, but I'm going to put a question mark. So I'm not going to try that one next. What I do want to try next is A NAND B, NAND A NAND B. See if that matches up with any of these over here. So A NAND B, A NAND B, and then we're going to have that, all that nonsense. A NAND B, NAND A NAND B. Okay, so let's remember A NAND B is 1110, 1110, 1110. And this is going to be, since they are matching rows, these are going to be false, 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 true. And does that help us? 0001? Sure, it does. Let's see, A and B. So AB equals that nonsense. And the gate writing would be, well, let's see, this might be a little sloppy. So to one side, I will do an AND gate, then I will cross the A. Maybe I'll do it in a different color so it doesn't get confused. And connect another NAND gate of these two, and then connect both of them in a NAND gate. And that's our diagram for only NAND gates to express A or B. That's our A and B. And finally, we want A or B. Well, let's see what happens. So our other permutation we wrote, well, this one's not going to be it. So this one we can cross off. We've done. And this one looks promising. So that's A NANDs on one side and B NANDs on the other. We make space in case it gets long. A NAND A, B NAND B, and then finally A NAND A NAND B NAND B. Okay, you get the point. But actually we don't know yet what's A NAND A. Well, let's see. A is 0011. A is 0011. So A NAND A is false, false, true, true. False, false, true, true. B is 0101. B B is 0, 1, 0, 1. Matches on the second and fourth column. So we have 1, 0, 1, 0. 1, 0, 1, 0. Okay, great. And now we look for the similar row, and we only have that on the first, and that's false. 0, 1, 1, 1. And is that what we want? Let's go back and check. It is what we want. So we can say A or B. A or B is equal to that. I won't write it out. And let's draw the diagram. A is going to double itself into this Nand gate. B is going to double itself into this Nand gate. And then we're going to have an AND gate like that. And that's a really, really complicated way of saying A or B.